Hello everyone, this is Amit Prambhat, a professor for CSC 208 Discrete Mathematics at Laurel Ridge Community College. Today we are going to continue on week 5's lecture series on multisets and multichoosing. We now enter into the third core section of multisets and multichoosing. Up to this point, our subsets have been strictly classical. Elements could not be repeated. But in real world, we frequently need to select collections of items where duplicates are perfectly fine. If you go to a bakery to buy a dozen donuts, you don't choose 12 unique flavors. You can buy 5 chocolate and 3 glazed and 4 jelly. To analyze these scenarios, we must define a new mathematical object, the multiset. So what is a multiset? A multiset is a generalization of a set where elements are allowed to appear multiple times, but the order of elements still does not matter. To distinguish them from standard sets, we often enclose them in angle brackets. For example, the set containing ABC is identical to the set containing AABC because standard sets ignore duplicates. However, multiset containing ABC is not equal to the multiset containing AABC. In a multiset, each element has an associated multiplicity, a count of how many times it occurs. Stars and bars technique. How do we count the number of k-element multisets we can build from a universe of n distinct options? We use a brilliant combinatorial technique called stars and bars. Imagine k selections we need to make as identical stars. We can separate these stars into n different categories using n-1 vertical bars. For example, any sequence of stars and bars represent a unique multiset choice. Because we are arranging a total of k stars and n-1 bars, the problem simplifies to choosing k positions out of a total k plus n-1 slots. This gives us our multi-choose formula. Let's apply the stars and bars formula to a concrete example. Suppose you want to buy 6 cans of soda from a machine that offers 8 different flavors. In this scenario, n equals 8, the number of categories, and k equals 6, the number of selections we are making. Applying our multi-choose formula, we calculate 8 plus 6 minus 1, choose 6, which simplifies to 13, choose 6. Working out the factorials, we discover that there are exactly 1,716 unique combinations of sodas you can bring home. This demonstrates how a seemingly complex repetition problem can be solved in seconds. Here is a table that shows how you can master counting table. The master counting table is one of the most important summaries of the course. It organizes the 4 core counting paradigms we have discussed. If order matters and repetition is allowed, we have lists n to the k. If order matters and repetition is forbidden, we have permutation. If order doesn't matter and repetition is forbidden, we have standard sets n choose k. And finally, if order doesn't matter but repetition is allowed, then we have multisets, counted by newly learned multi-choose formula. Master discrete and you can categorize any counting problem instantly. So let's move on to advanced sequences. With our foundational counting tools, firmly in place, we now transition to advanced sequences and combinatorial identities. In this section, we will explore how these counting formulas generate famous integer sequences that appear throughout nature, computer science, and advanced geometry. We will analyze triangular numbers, tetrahedral structures, binary string properties, and see how Pascal's triangle serves as a visual index for some of the most famous sequences in mathematical history. So let's talk about triangular numbers. It's denoted by Tn. These numbers represent the number of bowling pins or billiard balls required to form a perfect equilateral triangle of side length n. The formula for nth triangle number is n times n plus 1 divided by 2, which is equivalent to the binomial coefficient n plus 1 choose 2. If you look at Pascal triangle, the triangular numbers appear perfectly along the second diagonal. An interesting property, adding any two consecutive triangular numbers always yields a perfect square. Tetrahedral numbers. If we extend our geometric construction into 3 dimensions, we get tetrahedral numbers denoted by Te of n. These represent the number of spheres needed to build stable 3-dimensional triangular pyramid of base size n. The formula is given by binomial coefficient n plus 2, choose 3. In Pascal triangle, you can find these numbers along the third diagonal. For example, build pyramid of height 3. We stack a triangular layer of one sphere on top, 3 in the middle, 6 on the bottom, requiring total of 10 spheres. Identity subset as ones. Let's consider an elegant binary string identity. Suppose we ask how many binary strings of length n contain exactly k ones. To build such a string, we have n available slots, and we must choose exactly k of those slots to populate with a 1, leaving the remaining slots as zeros. Because the order in which we select the slots doesn't matter, this is a classic combination problem. The answer is simply n choose k. This shows how basic binomial coefficients serve as fundamental language of binary data storage. Double split pattern. Let's take a brief practical detour to see how these combinatorial ideas manifest in computer science, specifically in data processing. When parsing complex text records, programmers often use double split pattern. Imagine a log file where each record contains multiple email addresses separated by spaces, and we want to extract just the domain names. First, we split the record by the primary delimiter, the space, and then we take each email address and split it again by the secondary delimiter, the @ symbol. This nested subdivision is the direct computational equivalent of partitioning a set into subcategories. Binary string count. Let's visualize our binary mapping from slide 14 with a concrete example where n equals 4. As calculated by 2 raised to the 4th power, there are exactly 16 unique binary strings of length 4. If you group these strings by number ones that they contain, you'll find exactly one string with 0 ones, 4 string with 1 1, 6 strings with 2 ones, 4 strings with 3 ones and 1 string with 4 ones. Look at those counts 1, 4, 6, 4, 1. They are the exact coefficient of row 4 of Pascal's triangle. The algebra and geometry align perfectly. Euler's beautiful identity. While we are celebrating mathematical elegance, we must pause to look at Euler's identity. E raised to the I times pi plus 1 equals to 0. The legendary physicist Richard Feynman called this the most remarkable formula in mathematics. It seamlessly connects 5 of the most fundamental constants in all of the science: 0 and 1 from arithmetic, E from calculus, I from algebra, and pi from geometry. In combinatorics, we strive for the same level of unity, showing how visual, genomic, geometric paths, algebraic formulas, and concrete counting problems are all different expressions of single underlying reality. The Fibonacci pattern. Many people are surprised to learn that famous Fibonacci sequence is also packed inside Pascal's triangle. If you draw shallow diagonals across the triangle, starting at the edge and moving up one row and right column iteratively, and sum the numbers along those lines, you generate the Fibonacci numbers 1, 1, 2, 3, 5, 8, 13, and so on. This remarkable connection shows that the breeding patterns of rabbits, the spiral of pine cones, and binomial expression coefficients are all governed by same mathematical engine. Coin toss probabilities. Pascal's triangle is also an indispensable tool for calculating probability. If you toss a fair coin n times, the probability of getting exactly k heads is determined by the nth row of the triangle. For example, if you toss a coin 4 times, the total number of outcomes is 2 to the 4th, which is 16. The number of ways to get exactly 2 heads is given by row 4, column 2, which is 6. Thus, probability of 6 over 16 or 37.5%. The triangle allows you to calculate complex probabilities in your head without running simulations. Okay, we'll pause here and continue on for the next part of this lecture in the next video. Thank you.